Welcome to the Restful Stories. For as long as we have been human, we have tilted our heads back in the darkness and looked up, finding patterns in the chaos and telling stories about the lights in the sky. If you enjoy these explorations of the quiet and magnificent corners of our universe, please take a moment to subscribe so you can be notified of our future stories. Among all the brilliant points of light and familiar constellations, there are other, fainter things, cosmic ghosts that seem to hang just beyond our reach. Tonight, we journey towards one such object, a place that for millennia was nothing more than a curious, milky smudge in the heavens. It was a footnote in the star charts of ancient astronomers, a celestial cloud of unknown origin. But within that faint and distant glow lies a story of unimaginable scale, a narrative of cosmic collisions, of a trillion suns, and of a future that is intertwined with our own. It is a story that, once deciphered, shattered our entire conception of the universe and our place within it. So let us begin our journey there, to that silent and beautiful wonder. In the crisp, dark tapestry of the autumn sky, far beyond the familiar glitter of planets and the steadfast glow of the stars within our own cosmic home, lies a subtle, elongated smudge of light. To the unaided eye, it is an almost insignificant whisper, a faint and ghostly apparition easily lost to the glare of city lights or a passing veil of cloud. This ethereal patch, nestled within the embrace of the constellation that bears her name, is our gateway to a story of unimaginable scale, a narrative that begins in myth and ends at the very edge of our understanding of the universe. This is the Andromeda Galaxy. Its most common designation in the star charts of today is Messier 31, or sometimes NGC 224. But its soul is tied to a far older story. It is named for Andromeda, the princess of Ethiopia from Greek mythology, who was chained to a seaside cliff as a sacrifice to a sea monster, only to be saved by the hero Perseus. The constellation that houses this celestial wonder traces the outline of her bound form in the heavens, a permanent memorial to her plight and rescue. For millennia, this faint light was simply part of that celestial drama. It was not a place, but a feature, a curious celestial cloud whose true nature was utterly beyond comprehension. We now see it for what it is: a majestic spiral galaxy, a colossal Catherine wheel of stars, xa, and dust, a cosmic architecture it shares with our very own Milky Way. This makes it not just an object of study, but a kind of cosmic mirror. In its sweeping arms and glowing core, we can see a reflection of our own galactic home, a sibling city of stars that offers clues to our own past and future. It is our closest large galactic neighbor, the next great metropolis in the vast, dark ocean of intergalactic space. And yet, to speak of it as close is to stretch the meaning of the word to its breaking point. The light from Andromeda that graces our eyes on any given night began its journey across the void 2.54 million years ago. It has traveled continuously at the ultimate speed limit of the universe for a span of time that predates the emergence of modern humans on Earth. The photons striking your retina tonight left Andromeda when our distant ancestors were first shaping stone tools on the African plains. That immense gulf of space measures approximately 24 quintillion kilometers, or just under 15 quintillion miles. It is a distance so profound that it humbles our terrestrial measurements into meaninglessness. Despite this chasm, Andromeda holds a unique distinction. It is the most distant object that a human being can perceive without the aid of a telescope. It represents the farthest reach of the naked eye, a testament to the galaxy's sheer, overwhelming luminosity. For most of human history, its presence was noted, but not understood. The first known written record of this celestial cloud comes from the 10th century, in the year 964. The Persian astronomer Abd al-Rahman al-Sufi, a brilliant scholar working in the city of Isfahan, meticulously charted the heavens. In his seminal work, The Book of Fixed Stars, he described it as a small cloud, a lyrical and accurate description for the technology of his time. His work, a cornerstone of Islamic astronomy, preserved and expanded upon the knowledge of the ancient Greeks, ensuring that the faint smudge in Andromeda was not forgotten. For over 6 more centuries, that is what it remained. It was not until the dawn of a new age of discovery, in the year 1612, that human eyes saw it with newfound clarity. The German astronomer Simon Marius, a contemporary and rival of Galileo Galilei, pointed his simple refracting telescope towards the constellation. Through his primitive lens, the smudge resolved into a brighter, more concentrated glow, its core a soft, luminous pearl. While he could not discern its true nature as a galaxy of 1 trillion stars, his was the first telescopic observation, a pivotal moment that elevated the small cloud into a significant object of astronomical inquiry. A century and a half later, in the year 1771, it was catalogued by the famous French astronomer Charles Messier. Messier was, by trade, a comet hunter, and he grew increasingly frustrated by the stationary, fuzzy objects in the sky that looked like comets, but were not. To prevent himself and others from being repeatedly fooled, he began compiling a list of these celestial nuisances. The Great Cloud in Andromeda was the 31st entry on his list, and thus it became known as Messier 31. In his notes, Messier credited Simon Marius with its discovery, unaware of al-Sufi's far more ancient observation, a small but common type of error in the sprawling, interconnected history of science. This great island of stars is not adrift alone, however. It is the undisputed sovereign of our local cosmic neighborhood, a small swarm of galaxies gravitationally bound together known as the local group. This galactic family, spanning some 10 million light-years of space, consists of more than 50 galaxies, but most are tiny dwarf systems. The true heavyweights are few. Andromeda is the largest and most populous ember, the anchor of the entire system. Our own Milky Way is the second largest, followed by the smaller, but still substantial, Triangulum Galaxy. Together, these three spirals and their retinue of smaller satellite galaxies dance a slow, gravitational ballet, a cosmic story that has been unfolding for billions of years and will continue for billions more. The sheer scale of Andromeda is difficult to fully grasp, even in the abstract language of astronomy. Its visible disk, a sprawling expanse of spiraling starlight, stretches approximately 220,000 light-years from one edge to the other. To put that into perspective, if you were to travel at the speed of light, it would take you a full 220,000 years to cross from one side of the galaxy to the other. This makes its diameter more than twice that of our own Milky Way, which is estimated to be around 100,000 light-years across. This vast real estate is populated by an almost uncountable number of stars. Current estimates suggest that Andromeda is home to at least 1 trillion suns. This is a truly astronomical number, perhaps 2.5 to 10 times the estimated population of our own galaxy, which is thought to contain somewhere between 100 billion and 400 billion stars. This immense stellar population glows with a combined light that is 26 billion times brighter than our own sun. However, this vastness in size and stellar count presents a fascinating cosmic paradox. While it is larger and more populous, recent studies indicate that Andromeda may not actually be more massive than the Milky Way. The key to this riddle lies in the unseen. Astronomers now believe that our galaxy contains a significantly larger and more massive halo of dark matter, the mysterious, invisible substance that makes up the bulk of the universe's mass. So, while Andromeda may be the sprawling, luminous metropolis of the local group, the Milky Way might be the denser, heavier city, its true mass veiled in an invisible shroud. This gravitational heft dictates the ultimate fate of our local cosmic neighborhood. The two great galaxies of the local group are not static neighbors. For billions of years, they have been moving towards each other, drawn together by their mutual and inescapable gravitational attraction. Andromeda is hurtling towards the Milky Way at a tremendous velocity, closing the gap between us at a speed of approximately 110 kilometers per second, which is nearly 250,000 miles per hour. At this rate, it covers a distance equivalent to that between the Earth and the Moon in just over an hour. This inexorable approach is setting the stage for the most significant event in the future history of our galaxy. A colossal collision. In about 4.5 billion years, the outer spiral arms of Andromeda and the Milky Way will begin to interpenetrate. The night sky of any world within our galaxy at that time would be a spectacular, terrifying sight, with Andromeda's vast structure no longer a distant smudge, but a brilliant, distorted tapestry of light filling a huge portion of the heavens. This will not be a collision in the terrestrial sense, with stars crashing into one another. The distances between individual stars are so vast that direct impacts will be exceptionally rare. Instead, it will be a gravitational tidal wave. The two galaxies will pass through each other, their structures distorted and warped by the immense gravitational forces. Stars will be ripped from their original orbits and flung into long, looping streams, creating vestigial tails of light. The two galaxies will then pull apart, slow down, and inevitably fall back together for a second, and then a third passage. This process of merging will take hundreds of millions of years, a cosmic dance of destruction and creation. The end result of this galactic merger, after the dust settles and the gravitational chaos subsides, will likely be the birth of a new, even more massive galaxy. The beautiful, delicate spiral structures of both Andromeda and the Milky Way will be obliterated, their stars and gas clouds thoroughly scrambled and redistributed into a vast, featureless, elliptical, or lenticular shape. This future galactic behemoth has already been given a speculative nickname: Milkomeda. At the heart of Andromeda lies a region of extreme density and complexity, a core that is far from simple. Observations have revealed that it possesses what is known as a double nucleus. This is not to say it has two separate cores in the traditional sense, but rather that its central star cluster is oddly elongated, with two distinct concentrations of light. One of these concentrations, designated P1, is a bright, eccentric clump of stars orbiting the true center. The other, P2, is a fainter, more compact cluster that marks the actual gravitational heart of the galaxy. It is within this central point, P2, that Andromeda harbors its own supermassive black hole. This gravitational monster, an object of unimaginable density from which not even light can escape, is estimated to have a mass about 140 million times that of our own Sun, making it significantly larger than Sagittarius A, the 4 million solar mass black hole at the center of the Milky Way. It is the slint, invisible engine around which the entire galaxy, with its trillion stars, revolves. This complex and crowded core hints at a violent past, with the double nucleus structure possibly being the remnant of a smaller galaxy that was consumed by Andromeda long ago, its own core now forever orbiting within the heart of its conqueror. Andromeda is not just a solitary giant. It is the gravitational anchor for a whole family of smaller galaxies. It is orbited by a retinue of at least 14 known dwarf galaxies, small, gravitationally bound collections of stars that are caught in its immense gravitational well. These satellite galaxies are Andromeda's celestial courtiers, forever bound to their massive queen. Two of the most prominent of these companions are visible even with modest amateur telescopes. They are designated Messier 32 and Messier 110. M32 is a compact, bright, elliptical dwarf galaxy that appears as a small, fuzzy star right next to Andromeda's core. M110 is a larger, more diffuse elliptical dwarf located a little farther out from the main disk. These companions are not passive observers. Their own gravity, though small in comparison, has a tangible effect on Andromeda. Their constant tidal tugging helping to warp and shape its grand spiral arms over the eons. The core of Andromeda is not just home to a black hole. It is also dominated by a massive, incredibly dense star cluster. This is the most tightly packed globular cluster in the entire local group. Within this central region, the concentration of stars is staggering. The light from hundreds of thousands of suns is crammed into a space only a few light years across, creating a stellar environment of unimaginable brilliance and intensity. A place where the concept of a dark night sky would be utterly alien. The grand and elegant spiral structure of Andromeda, a defining feature of its majestic appearance, is a canvas painted by both internal dynamics and external forces. Its beautiful arms, swirling lanes of young, bright blue stars, gasa, and dust, are not as pristine and symmetrical as they might appear from our distant vantage point. They are being actively distorted, their graceful curves pulled and twisted out of shape by the relentless gravitational influence of its closest companions. The two dwarf galaxies, Messier 32 and Messier 110, orbit in relatively close proximity to Andromeda's main disk. As they plow through the galaxy's extended halo, their own gravity exerts a constant tidal pull on the stars and gas clouds in the spiral arms. This interaction creates subtle warps and ripples in the disk, disrupting the perfect symmetry of the spiral pattern. It is a slow, cosmic sculpting process that has been shaping Andromeda's appearance for billions of years. A constant reminder that even the largest structures in the universe are not immune to the influence of their smaller neighbors. The visual evidence of these interactions is compelling. Detailed observations of Andromeda have revealed that it possesses at least two major spiral arms, along with a prominent and intriguing ring of dust. This dust ring, a vast, dark circle silhouetted against the bright glow of the galaxy's central bulge, is a feature not seen in our own Milky Way. Its origin has been a subject of intense study, with many astronomers believing it to be the direct result of a past cosmic collision. The leading theory suggests that the compact dwarf galaxy, Messier 32, may have plunged directly through the main disk of Andromeda over 200 million years ago. This dramatic, high-speed passage would have acted like a stone dropped into a cosmic pond, sending a powerful density wave rippling outwards through the gas and dust of Andromeda's disk. This wave would have compressed the interstellar medium, triggering a burst of star formation and sweeping dust into the distinct ring-like structure we see today. If this theory is correct, the dust ring is not just a feature, but a scar, a beautiful, large-scale piece of evidence of Andromeda's violent and dynamic history. Beyond its two most prominent companions, Andromeda is the gravitational master of a much larger court. Astronomers have so far identified at least 14 distinct dwarf galaxies that are gravitationally bound to it, orbiting the larger galaxy like planets around a star. These satellite galaxies are the surviving remnants of the smaller building blocks from which Andromeda itself was formed over billions of years. They come in various shapes and sizes, from compact ellipticals like Messier 32 to more diffuse and faint spheroidal systems. Each one is a small, self-contained universe of millions or even billions of stars, their fates now inextricably linked to the gravitational whims of their massive host. Their orbits are long and looping, taking them on journeys of hundreds of thousands of light years, sometimes plunging them through Andromeda's halo, and at other times carrying them far out into the intergalactic void before they are pulled back. These satellites are crucial for understanding the distribution of dark matter around Andromeda, as their orbital speeds and paths are dictated by the total mass of the system, most of which is invisible. Among this retinue of satellite galaxies, two stand out for their size and brightness, making them observable to amateur astronomers on Earth. As mentioned, these are Messier 32 and Messier 110. M32 is a fascinating object in its own right. It is a very compact elliptical galaxy, a dense ball of old reddish stars. Its extreme density and lack of gas or dust suggest that it has been stripped of its outer layers by close encounters with Andromeda, leaving only its tightly bound core behind. M110, in contrast, is a much more diffuse dwarf elliptical galaxy. It is larger than M32, but has a much lower surface brightness, giving it a more ghostly appearance. Unlike M32, it shows some signs of recent, albeit minor, star formation, and possesses a faint dusting of interstellar dust, suggesting it has not been as thoroughly tidally stripped by its giant neighbor. These two companions provide a contrasting view of the life of satellite galaxies, one ravaged by its interactions, and the other still retaining some of its original character. But the family of galaxies in our local neighborhood may be even more interconnected. The Triangulum Galaxy, also known as Messier 33, is the third largest member of the local group. It is a beautiful, face-on spiral galaxy, smaller than both the Milky Way and Andromeda, but still a substantial system of about 40 billion stars. For a long time, it was considered an independent galaxy, a distant third player in the local group's dynamics. However, recent, more precise measurements of its motion through space suggest that it may, in fact, be a satellite of Andromeda. Its trajectory indicates that it is likely gravitationally bound to its much larger neighbor, making it the largest satellite galaxy in the known universe. If this is true, the Andromeda system is even more magnificent than previously thought. A galactic empire ruled by a trillion-star sovereign with a major spiral galaxy as its most prominent vassal. Amidst the swirling disk and glowing halo of Andromeda, there are ancient, self-contained cities of stars known as globular clusters. These are dense, spherical collections of hundreds of thousands or even millions of very old stars, all born together from the same cloud of gas in the very early universe. They are cosmic fossils, providing a direct window into the conditions of the galaxy's distant past. The Milky Way has about 150 of these ancient clusters, but Andromeda is far richer. Astronomers have identified more than 450 globular clusters orbiting within its halo. This vast population of ancient stellar systems is a testament to Andromeda's more active and tumultuous early history, a period when it likely consumed more small, gas-rich galaxies than our own, each contributing its own set of globular clusters to the growing giant. Within this impressive collection, one cluster reigns supreme. It is known as Mayal 2, or sometimes Globular 1, abbreviated as G1. This is the most massive and luminous globular cluster in the entire local group. It is a colossal ball of several million stars shining with a brilliance that outshines any globular cluster in our own galaxy. In fact, it is at least twice as luminous as Omega Centauri, the brightest and most massive globular cluster orbiting the Milky Way. G1 is so massive that some astronomers have speculated it may not be a true globular cluster at all, but rather the stripped-down core of a dwarf galaxy that was cannibalized by Andromeda long ago, its outer stars torn away to leave only this incredibly dense, bright remnant behind. The central region of Andromeda, its glowing bulge of tightly packed stars, is another area where it differs significantly from our own galaxy. The central bulge of Andromeda is considerably larger and more massive than that of the Milky Way. This suggests a different formation history. Large galactic bulges are thought to be built up over time through violent mergers and collisions. The larger bulge of Andromeda implies that it has experienced more of these major merger events in its past than the Milky Way has. contributing to its larger size and more dominant central core. This turbulent history has left its mark not only in the size of the bulge, but also in the motions and ages of the stars that reside there. This crowded, ancient heart of the galaxy is also a surprisingly dynamic and dangerous place. Recent surveys using the Chandra X-ray Observatory have peered into this dense stellar environment and uncovered a remarkable population of black hole candidates. 7 of the 35 known black hole candidates in the entire Andromeda Galaxy are located within just 1,000 light-years of the galactic center. These are not supermassive black holes, but smaller, stellar mass black holes, the collapsed remnants of giant stars that died in supernova explosions. Their concentration in the core is a result of a process called mass segregation, where heavier objects in a star system tend to sink towards the gravitational center over time. What is particularly striking is the environment in which these black holes are found. In our own Milky Way, despite extensive searches, no black holes have ever been conclusively identified within a globular cluster. It was thought that they would be ejected by complex gravitational interactions. However, in Andromeda, the story is different. A surprising 8 of the 9 black hole candidates that have been found within globular clusters in the entire galaxy are located in Andromeda's clusters. This discovery challenges our models of how black holes and star clusters interact and evolve, suggesting that the dense, ancient environments within Andromeda's globulars are somehow more hospitable to retaining their black holes than those in our own galaxy. Finally, when we turn our gaze towards Andromeda, either with the naked eye or a telescope, its brightness is one of its most defining characteristics. This is quantified by astronomers using a scale called apparent magnitude. The Andromeda Galaxy shines with an apparent magnitude of plus 3.44. This makes it one of the brightest objects in Charles Messier's famous catalogue, easily visible from a dark sky location, and a truly stunning sight through a simple pair of binoculars, revealing its elongated shape and bright, glowing core that has captivated astronomers for centuries. The visibility of the Andromeda Galaxy from Earth is a matter of celestial mechanics and geographic fortune, a seasonal spectacle that graces the night skies for those willing to look. For observers in the Northern Hemisphere, the best time to view this distant island universe is during the autumn and winter months. From late August through February, the constellation of Andromeda rides high in the evening sky, carrying its faint, fuzzy treasure with it. During the peak of this viewing season, around November, the galaxy culminates, reaching its highest point in the sky around midnight. At this time, its faint light has to travel through the least amount of Earth's obscuring atmosphere, making it appear brighter and clearer than at any other time of the year. It is a prime target for stargazing parties and a favorite subject for astrophotographers who take advantage of the long, dark nights of winter to capture its delicate details. For those in the southern hemisphere, the opportunity to see Andromeda is more fleeting and challenging. The galaxy appears much lower in the northern sky, skimming just above the horizon for a shorter period. The optimal viewing window for southern observers is from October through December. But even then, its low altitude means its light is often dimmed and distorted by atmospheric turbulence. Finding such a faint object requires a clear, dark night and a bit of celestial navigation. Fortunately, the heavens provide a convenient and unmistakable guidepost. The constellation of Cassiopeia, with its distinctive W or M shape formed by 5 bright stars, is one of the most easily recognizable patterns in the northern sky. This celestial W serves as an excellent pointer. By following the direction indicated by the 3 easternmost stars of the W, an observer can trace a line across the sky that leads directly to the location of the Andromeda Galaxy. Using this simple star-hopping technique, even a novice skywatcher can locate this faint patch of light, a ghostly glimmer that represents a trillion suns. While we have studied Andromeda from afar for centuries, the possibility of studying worlds within it has long been confined to the realm of science fiction. However, in the year 1999, a remarkable and tantalizing observation offered the first hint that Andromeda may host its own planets. An astronomical event known as a microlensing event, designated PA 99N2, was detected. Microlensing occurs when a massive object, such as a star, passes directly in front of a more distant star from our point of view. The gravity of the foreground star acts like a lens, bending and magnifying the light of the background star, causing it to brighten temporarily in a very specific and predictable way. In this particular case, a star within the Andromeda Galaxy was observed to brighten. But the pattern of the brightening was unusual. There was a smaller, secondary peak in the light curve, a telltale sign that the lensing star was not alone. This secondary peak suggested the presence of a smaller, unseen companion orbiting the lensing star, a companion whose own gravity was contributing to the lensing effect. Based on the details of this event, if this companion is indeed a planet, it would be the very first one ever discovered in another galaxy. The data from the microlensing event allowed astronomers to make an estimate of the potential exoplanet's mass. The calculations suggested a massive world, a gas giant approximately 6.34 times the mass of Jupiter, our own solar system's largest planet. A world of this size would be a true behemoth, a colossal gas giant dwarfing anything in our own planetary family. The discovery remains a candidate, as microlensing is a one-time event. The precise alignment of the 2 stars will not happen again in our lifetimes, making follow-up observations impossible. Nevertheless, the event PA 99N2 stands as a landmark observation, a tantalizing clue that planetary systems, a common feature of our own Milky Way, are likely just as ubiquitous in the grand spiral of Andromeda. The very existence of Andromeda, this colossal structure of stars and gas, prompts a fundamental question. Where did it come from? The current understanding of galaxy formation, based on the lambda cold dark matter model of cosmology, suggests that large galaxies like Andromeda are not born in their final, majestic form. Instead, they are built up over billions of years through a process of hierarchical assembly. In the early universe, small, irregular proto-galaxies formed from vast clouds of hydrogen and helium gas. Over cosmic time, these smaller systems were drawn together by gravity, colliding and merging to form progressively larger and larger galaxies. Scientists believe that the Andromeda Galaxy we see today is the product of such a violent and creative history. By studying the ages and motions of the stars within its halo and disk, they have pieced together a likely timeline. The evidence suggests that Andromeda was formed from the cataclysmic collision and subsequent merger of two smaller, but still substantial galaxies. This formative event is thought to have occurred sometime between 5 and 9 billion years ago. This titanic merger would have been the single most important event in Andromeda's history, a chaotic and spectacular process that triggered massive bursts of star formation, scrambled the orbits of existing stars, and ultimately settled into the grand spiral structure we observe today. The remnants of this ancient collision can still be seen in the complex structure of Andromeda's halo and the intricate motions of its oldest stars. When we view Andromeda in the visible light our eyes can see, we are seeing the combined glow of its trillion stars. But when we observe it through different kinds of light, using specialized telescopes, hidden details and new structures emerge. When the Andromeda Galaxy is viewed in ultraviolet light, a wavelength of light that is invisible to the human eye, but traces the presence of young, hot, massive stars, its appearance changes dramatically. The familiar, sweeping spiral arms seem to fade, and instead, the galaxy's disk is dominated by a series of concentric rings. These vast, circular structures of intense star formation are not apparent in visible light, but are the most prominent features in the ultraviolet. These rings are another piece of the puzzle of Andromeda's violent past. They are believed to be fossil evidence of a more recent collision, a cosmic impact that sent shock waves propagating through the galaxy's disk. As discussed, the prime suspect for this collision is the dwarf elliptical galaxy Messier 32. The prevailing theory suggests that over 200 million years ago, M32 made a high-speed bullseye passage through the plane of Andromeda's disk. This plunging orbit created a powerful, ring-like density wave that expanded outwards, much like the ripples on a pond. As this wave traveled through the interstellar gas in Andromeda's disk, it compressed the gas, triggering a massive wave of star birth. The young, hot, and massive stars that were born in this event shine brightly in ultraviolet light, creating the spectacular ring-like structures that telescopes like NASA's Galaxy Evolution Explorer have observed. To truly appreciate the scale and detail of our galactic neighbor, one needs a camera with a truly cosmic perspective. The Hubble Space Telescope, orbiting high above the blurring effects of Earth's atmosphere, has provided humanity with its sharpest views of the universe. In a monumental undertaking, Hubble was used to create the largest and most detailed composite image of the Andromeda Galaxy ever assembled. This image, a mosaic stitched together from hundreds of individual photographs, contains an astounding 1.5 billion pixels. To view it at full resolution would require more than 600 high-definition television screens. This panoramic view covers a vast swath of Andromeda's disk, stretching over 40,000 light-years, from its dense central core out to its sparser outer regions. Within this single, breathtaking image, astronomers have been able to resolve over 100 million individual stars. It is a stellar census on an unprecedented scale, allowing scientists to study the different populations of stars, from young blue giants to old red dwarfs, across different regions of the galaxy. The image also revealed thousands of star clusters, tight-knit families of stars born together, as well as vast, dark lanes of interstellar dust, the raw material for future generations of stars. This Hubble panorama is not just a pretty picture. It is a rich scientific dataset that will be studied by astronomers for decades to come, offering unparalleled insights into the structure and evolution of a spiral galaxy that serves as our cosmic twin. The Hubble Space Telescope's magnificent panoramic image of Andromeda, with its staggering detail, revealed not just a static portrait, but a dynamic and evolving cityscape of stars. Within that vast mosaic, astronomers could discern over 100 million individual points of light, each a sun in its own right, and thousands of distinct star clusters, glowing knots of stellar siblings born from the same natal clouds. This unprecedented deep dive into Andromeda's stellar populations provided a treasure trove of data, allowing for detailed studies of stellar evolution, the distribution of different types of stars, and the history of star formation across the galaxy's sprawling disk. It is a resource that continues to yield new discoveries, a digital window into the inner life of our galactic neighbor. The sheer beauty and scientific richness of Andromeda have made it a perennial favorite, a celestial celebrity, not just for professional astronomers, but for the global community of amateur skywatchers and astrophotographers. For amateur astronomers, it represents a satisfying challenge and a rewarding sight. Finding its faint, ethereal glow in the night sky is a rite of passage, a connection to the vastness of the cosmos that can be achieved with nothing more than a pair of binoculars or a small backyard telescope. Through the eyepiece, the galaxy transforms from a faint smudge into a distinct oval of light, its core shining with a concentrated brilliance, hinting at the trillion stars held within. For astrophotographers, Andromeda is a premier target, a vast and complex canvas on which they can practice their craft. Capturing its delicate spiral arms, the dark dust lanes, and the subtle colors of its star populations requires patience, skill, and sophisticated equipment. The resulting images, often the product of many hours of exposure time, are not just beautiful works of art, but can also be scientifically valuable. Tracking changes like the occasional brightening of a variable star or the faint glow of a nova. This passionate community of citizen scientists contributes to our collective appreciation and understanding of this distant stellar metropolis. The profound scientific value of Andromeda stems from a simple but crucial fact. It is the closest large spiral galaxy to our own. This makes it an unparalleled cosmic laboratory for studying the processes of galaxy formation and evolution. While we reside within the Milky Way, our view of our own galaxy is fundamentally limited. We are stuck inside it, our perspective obscured by vast clouds of interstellar dust that block our view of the galactic center and the far side of the disk. It is like trying to understand the layout of a city while standing in the middle of a crowded street. Andromeda, however, we can see in its entirety, a grand spiral laid out before us from an external vantage point. We can study its overall structure, its bulge, its disk, its halo, and the intricate details of its spiral arms in a way that is simply impossible for our own galaxy. By studying Andromeda, we can infer a great deal about the Milky Way, its stellar populations, its star formation rate, its merger history, and the properties of its central black hole all provide a crucial context for understanding our own cosmic home. It is our control group, our cosmic twin, and the insights we gain from studying its life story help us piece together the biography of our own galaxy. The motion of Andromeda is a complex dance on a cosmic scale, a combination of its journey through space and our own motion around the Sun and within the Milky Way. We know it is moving towards us, but the speed of its approach depends on our frame of reference. When measured relative to our Sun, the Andromeda Galaxy is closing the distance at a breathtaking speed of approximately 300 kilometers per second, or about 670,000 miles per hour. This blue shift, the compression of its light waves as it moves towards us, was one of the first indications that some nebula were in fact other galaxies, and that the universe was a dynamic place. This high velocity is a combination of Andromeda's own motion towards the Milky Way and our Sun's own rapid orbit around the center of our galaxy. It is a testament to the powerful gravitational forces that govern the local group, pulling its largest members towards their ultimate destiny. While the visible disk of Andromeda is vast, it is merely the bright, central portion of a much larger and more ghostly structure, the stellar halo. This is a vast, roughly spherical region of space that surrounds the entire galaxy, populated by a sparse scattering of old stars and ancient globular clusters. Recent, incredibly deep and sensitive surveys have revealed that Andromeda's halo is far larger and more complex than previously imagined. It extends over 1 million light-years out from the galactic center, a colossal sphere of influence that stretches halfway to our own Milky Way. This halo is not a smooth, uniform cloud of stars. Instead, it is riddled with immense streams and clouds of stars, vast, river-like structures that are the shredded remnants of smaller dwarf galaxies that Andromeda has consumed over billions of years. These stellar streams are the archaeological evidence of Andromeda's galactic cannibalism, tracing the final, dying orbits of the smaller galaxies it has absorbed. The complexity and sheer size of this halo suggest that Andromeda has had a more violent and active merger history than our own galaxy, growing to its current massive size by systematically devouring its smaller neighbors. The stars that populate this vast halo are fundamentally different from those in the bright, flat disk of the galaxy. They are, on the whole, much older, among the first generations of stars to form in the universe. They also contain far fewer heavy elements, a property astronomers refer to as low metallicity. This is because they were born from the pristine hydrogen and helium gas that filled the early universe, before many generations of stars had a chance to forge heavier elements like carbon, oxygen, and iron in their nuclear furnaces and disperse them through supernova explosions. The stars in the disk, by contrast, are younger and more metal-rich, having formed from gas that has been progressively enriched by countless stellar life cycles. This clear distinction between the halo and disk populations provides a crucial timeline for the galaxy's formation, showing how it was built from the inside out, first forming a vast, ancient halo, and then gradually settling into a more orderly, star-forming disk. One of the most significant differences between Andromeda and the Milky Way is their current level of star-forming activity. While our galaxy is a relatively active stellar nursery, constantly churning out new stars in its spiral arms, Andromeda is in a more quiescent phase of its life. It has a very low rate of star formation compared to the Milky Way. Its vast reservoirs of cool hydrogen gas, the essential fuel for creating new stars, are surprisingly depleted. This suggests that its most vigorous period of star birth is in its past. While the Milky Way is still building up its stellar population at a steady pace, Andromeda appears to be slowly winding down, a mature galaxy that is coasting on the stellar population it built up billions of years ago. Another key structural difference lies at the very heart of the two galaxies. The Milky Way is classified as a barred spiral galaxy, meaning its central bulge is elongated into a distinct bar-like structure of stars. This bar acts like a cosmic funnel, channeling gas from the inner disk towards the central supermassive black hole. Andromeda, however, appears to have a much less prominent, or perhaps even non-existent, central bar. Its core is dominated by a large, classical bulge of old stars, a more rounded and less dynamic structure. This structural difference has profound implications for how the two galaxies evolve, how they feed their central black holes, and how they distribute gas and trigger star formation in their central regions. In the grand chemical census of the universe, Andromeda also stands apart. It has a higher metallicity than the Milky Way. This means that, on average, its stars and gas clouds contain a higher proportion of elements, heavier than hydrogen and helium. This is somewhat counterintuitive, given its lower current star formation rate. It suggests that Andromeda's past star formation was incredibly efficient and vigorous, rapidly enriching its interstellar gas with heavy elements early in its history. This different chemical makeup affects everything from the color of its starlight to the way new stars and planets form within it. Finally, the vast stellar disk of Andromeda is not perfectly flat like a spinning record. Sensitive observations of the motions of its stars and gas have revealed that the disk is significantly warped, much like the brim of a fedora hat. One side of the disk is bent upwards, while the opposite side is bent downwards. This warping is almost certainly the result of ongoing gravitational interactions with its satellite galaxies, particularly Messier 32 and Messier 110. As these smaller galaxies orbit Andromeda, their gravity tugs on the outer edges of the disk, pulling the stars and gas out of a perfectly flat plane and creating the large-scale warp that we observe today. It is a dynamic, living structure, constantly being shaped and reshaped by the gravitational dance of its entire galactic family. Our view of the Andromeda Galaxy is a matter of cosmic alignment, a fortunate but specific perspective that shapes how we perceive its structure. The galaxy is not presented to us perfectly face-on, like a wheel laid flat, nor is it perfectly edge-on, like a thin line of light. Instead, it is tilted at a significant angle relative to our line of sight. Astronomers have calculated this angle of inclination to be approximately 77 degrees. An inclination of 0 degrees would mean we are looking straight down on its spiral face, while 90 degrees would mean we see it precisely edge on. At 77 degrees, Andromeda is tilted enough that we have a clear, panoramic view of its overall spiral structure. But it is also foreshortened, making the galaxy appear more elliptical than it actually is. This particular orientation is a boon for astronomers, as it allows them to study both the distribution of stars and gas across its disk and the vertical structure of its central bulge and halo, offering a more three-dimensional perspective than a purely face-on view would allow. The life of a galaxy is punctuated by moments of extreme violence and brilliance. the explosive deaths of massive stars known as supernovae. These cataclysmic events are responsible for creating many of the heavy elements in the universe and are a key driver of galactic evolution. Based on its size and stellar population, astronomers estimate that the Andromeda Galaxy should experience, on average, about one supernova explosion every 300 to 400 years. This is a relatively low rate, consistent with its overall low level of current star formation, as the most common type of supernova arises from the death of young, massive stars. Despite this expected rate, in over 4 centuries of telescopic observation, humanity has witnessed only one confirmed supernova in Andromeda. This historic event occurred in the year 1885. A new, bright star suddenly appeared near the galaxy's core, shining with a luminosity that rivaled the entire central bulge. Initially, many observers thought it was a nova, a much smaller and more common stellar eruption, but within our own Milky Way. At the time, the true nature of Andromeda as a separate galaxy was not yet known. This star, which was given the designation S Andromedae, was the first and, to this day, the only supernova ever observed in another galaxy. It was a pivotal, though not fully understood at the time, observation. Its extreme brightness was a major clue that the Andromeda Nebula, as it was then called, was a far more distant and grander object than anyone had previously imagined. If it were a simple nova within our own galaxy, it would not have appeared so brilliant. The light from S Andromeda that reached Earth in 1885 had been traveling for 2.5 million years, a silent testament to the vast scale of the cosmos that would only be fully appreciated decades later. Within the diverse stellar populations of Andromeda, there are peculiar stars that seem to defy the standard models of stellar evolution. Among these are the blue stragglers, a significant population of which has been identified in Andromeda's central bulge and globular clusters. These stars are a cosmic puzzle. They are found in regions dominated by very old stars, yet they appear anomalously hot, blue, and massive, characteristics typical of much younger stars. Their name comes from the fact that they seem to be straggling behind their elderly neighbors on diagrams that plot stellar age and color. The most widely accepted explanation for their youthful appearance is that they are the product of stellar mergers, or collisions. In the incredibly dense star fields near Andromeda's core, 2 old, small, reddish stars can, over billions of years, collide and merge, or a star in a binary system can slowly siphon mass from its companion. The resulting merged star is more massive than either of its progenitors, causing it to burn its nuclear fuel at a much higher temperature, giving it a new lease on life and a deceptive, youthful blue glow. The abundance of these blue stragglers in Andromeda provides crucial clues about the dynamics of its dense stellar environments. Andromeda is also a rich source of high-energy radiation, much of it emanating from exotic binary star systems. It hosts a large number of X-ray binaries, systems where a compact object, either a neutron star or a stellar mass black hole, is locked in a tight orbit with a normal, companion star. The immense gravity of the compact object pulls a stream of gas from its companion. This gas spirals inwards, forming a superheated accretion disk around the black hole or neutron star. As the gas is heated to millions of degrees by friction and gravitational forces, it emits intense X-rays, making these systems some of the brightest X-ray sources in the sky. The Chandra X-ray Observatory has identified hundreds of these point-like sources within Andromeda. Their distribution and properties help astronomers understand the endpoints of stellar evolution, the formation of black holes, and the life cycle of binary systems in a different galactic environment. Perhaps one of the most profound discoveries about Andromeda, and indeed all spiral galaxies, came from studying the way it rotates. By measuring the Doppler shift of light from its stars and gas clouds, astronomers can determine how fast different parts of the galaxy are spinning. One would expect that stars in the outer regions of the galaxy, far from the gravitational pull of the concentrated mass at the center, would orbit much more slowly than stars closer in, just as the outer planets in our solar system orbit the Sun more slowly than the inner planets. However, when astronomers measured Andromeda's rotation curve, they found something completely unexpected. The orbital speed of the stars did not decrease with distance from the center. Instead, it remained remarkably constant, or flat, all the way out to the visible edge of the disk. This observation was a clear and startling violation of Kepler's laws of motion. The only way to explain this was if there was a vast amount of unseen mass, a massive, invisible halo of matter extending far beyond the visible stars, whose gravity was holding the galaxy together and keeping the outer stars orbiting at such high speeds. This was one of the first and most compelling pieces of evidence for the existence of dark matter. The flat rotation curve of the Andromeda Galaxy remains a classic textbook example of the overwhelming evidence for this mysterious, invisible substance that constitutes about 85% of the matter in the universe. While its gravitational field is immense, the magnetic field of the Andromeda Galaxy is far more subtle. Using radio telescopes to observe the polarized emission from cosmic rays spiraling within the galaxy, astronomers have been able to map its large-scale magnetic field. The field lines appear to be arranged in a coherent, ring-like structure, following the spiral arms. The overall strength of this magnetic field is incredibly weak, about 1/millionth the strength of Earth's own magnetic field. Despite its weakness, this field plays a crucial role in the galaxy's ecosystem. It helps to guide the flow of interstellar gas. It influences the formation of new stars by providing support against gravitational collapse in gas clouds, and it confines high-energy cosmic rays within the galactic disk. The space between the stars in Andromeda is not empty. It is filled with a tenuous mixture of gas and dust known as the interstellar medium. This is the raw material from which new stars are born, and the repository for material ejected by dying stars. Studies of this medium in Andromeda reveal that it is, on average, colder and less turbulent than the interstellar medium of our own Milky Way. This is consistent with Andromeda's lower rate of star formation. The formation of massive stars and their subsequent supernova explosions are the primary drivers of turbulence in a galaxy, heating the gas and churning it with powerful shock waves. With fewer of these events occurring, Andromeda's interstellar medium has settled into a more quiescent state. This calmer environment affects how new generations of stars will form, likely leading to a slower and less chaotic process of star birth than that seen in our own more active galaxy. From our distant perspective, the Andromeda Galaxy presents an image of remarkable order and regularity. Its overall structure appears very smooth, with a well-defined central bulge and gracefully unwinding spiral arms. This is in contrast to the Milky Way, which is thought to have a more clumpy and irregular structure, with a more prominent central bar and more fragmented, less coherent spiral arms. This difference in appearance is likely a reflection of their different recent histories. The Milky Way has had more recent and ongoing interactions with smaller satellite galaxies, such as the Large and Small Magellanic Clouds, which have perturbed its disk and created a more chaotic structure. Andromeda's smoother appearance suggests a more tranquil recent past, with its last major merger having occurred billions of years ago, allowing its disk to settle into a more stable and orderly configuration. The chemical composition of a galaxy, its specific blend of elements, is its unique fingerprint, a record of its entire history of star formation. When astronomers analyze the light from Andromeda's stars and gas, they find a different abundance pattern of elements compared to what we see in the Milky Way. Specifically, the Andromeda Galaxy has a higher ratio of what are known as alpha elements, such as oxygen and magnesium, relative to iron. Alpha elements are primarily produced in the supernova explosions of massive, short-lived stars, while a significant fraction of iron is produced in a different type of supernova involving white dwarf stars, which occur on much longer timescales. The higher alpha to iron ratio in Andromeda suggests that its major period of star formation was more rapid and occurred earlier in its history than the Milky Way's. It formed a large number of massive stars very quickly, enriching its gas with alpha elements, and then its star formation rate declined before a large amount of iron could be produced by the longer-lived systems. This chemical evidence provides another strong clue that Andromeda grew up faster and earlier than our own galaxy. The sheer scale and tantalizing proximity of the Andromeda Galaxy have made it a fertile ground for the human imagination, a celestial landmark in the landscape of speculative fiction. For decades, it has served as a go-to destination for stories of interstellar travel, alien empires, and cosmic conflict. In countless science fiction novels, television shows, and films, Andromeda is depicted as the home of ancient, hyper-advanced alien civilizations, sometimes benevolent guides, other times existential threats to humanity. This recurring motif taps into a deep-seated human curiosity about our place in the universe and the possibility of life beyond Earth. As the only other great galaxy visible to the naked eye, it represents a tangible other, a destination that feels almost within reach, despite the millions of light years that separate us. It has become a symbol of the unknown, a cosmic shorthand for a setting that is at once magnificent, mysterious, and profoundly alien. This tradition has cemented Andromeda's place not just in astronomical catalogs, but in our shared cultural consciousness as a place of wonder and adventure. For much of astronomical history, Andromeda's identity was shrouded in ambiguity, a confusion reflected in its early nomenclature. In older astronomical texts and star charts, it was almost universally referred to as the Great Andromeda Nebula. The term nebula, from the Latin word for cloud, was a catch-all designation for any fuzzy, extended object in the night sky that was not a planet or a comet. This included everything from glowing clouds of gas within our own galaxy, like the Orion Nebula, to distant star clusters. The true nature of these objects was one of the greatest astronomical mysteries of the 19th and early 20th centuries. Andromeda, being the brightest and most prominent of these spiral nebulae, was at the very center of this debate. It appeared as a swirling, cloud-like structure, and without the ability to resolve its individual stars, it was impossible to tell if it was a nearby cloud of gas or something far more profound. This period of uncertainty culminated in one of the most famous public debates in the history of science. In the year 1920, the astronomical community was deeply divided on the issue of the scale of the universe. This division was publicly aired in what came to be known as the Great Debate, held at the Smithsonian Museum of Natural History in Washington, D.C. The two main protagonists were Harlow Shapley of the Mount Wilson Observatory and Heber Curtis of the Lick Observatory. Shapley argued passionately that the universe was composed of a single, vast galaxy, our own Milky Way, and that spiral nebulae like Andromeda were merely nearby gas clouds contained within it. He had recently shown that the Milky Way was far larger than previously thought, and he believed it constituted the entirety of the cosmos. Curtis, on the other hand, championed the island universe hypothesis, proposing that the spiral nebulae were in fact other galaxies, vast and distant stellar systems comparable in size and scale to our own Milky Way. He pointed to the dark dust lanes in Andromeda, which resembled the dust lanes in our own galaxy, and the faint novae that had been observed within it, suggesting they were too dim to be nearby objects. The debate was spirited, but ultimately inconclusive. as neither side had the definitive evidence needed to prove their case. The resolution to this profound cosmic question came just a few years later, thanks to the work of the astronomer Edwin Hubble. Using the new 100-inch Hooker telescope at the Mount Wilson Observatory, the most powerful telescope in the world at the time, Hubble was able to do what no one before him could. He resolved individual stars in the outer arms of the Andromeda Nebula. This was a monumental achievement in itself, but Hubble went a crucial step further. He identified a specific type of pulsating star known as a Cepheid variable. These stars are cosmic lighthouses. Their intrinsic brightness is directly related to the period of their pulsations. By measuring the pulsation period of a Cepheid, an astronomer can determine its true luminosity. By then comparing its true luminosity to its apparent brightness as seen from Earth, one can calculate its distance with remarkable accuracy. Hubble identified several Cepheid variables in Andromeda and performed the calculation. The result was staggering. He determined that Andromeda was nearly 1 million light-years away, a distance that placed it far, far outside the most generous estimates for the boundaries of the Milky Way. His definitive measurement, presented in 1925, settled the great debate once and for all. Andromeda was not a nebula. It was another galaxy. In that single moment of discovery, the known universe expanded by an unimaginable factor. The realization that our galaxy was just one of many, perhaps billions, of island universes scattered across the vastness of space was a scientific and philosophical revolution, a profound recalibration of humanity's place in the cosmos. At the heart of Andromeda's serene and ancient bulge lies a core that, compared to many other galaxies, is remarkably calm. Its supermassive black hole is a sleeping giant. Many galaxies possess what are known as active galactic nuclei, or AGN, where the central black hole is voraciously consuming vast amounts of gas and dust. This infalling material forms a brilliant, superheated accretion disk that can outshine the entire galaxy combined. Andromeda, however, has a very quiescent and inactive nucleus. The amount of material trickling down into its central black hole is minimal, resulting in a core that is millions of times fainter than that of an active galaxy. This quiescence is another piece of evidence that Andromeda's most turbulent and formative years are behind it. Its central regions have been largely cleared of the gas and dust that would otherwise fuel its central engine, leaving it in a state of peaceful retirement. The vast, ghostly halo of stars that envelops Andromeda is not a uniform sphere, but a lumpy, complex structure filled with the echoes of past meals. Deep and sensitive imaging has revealed that this halo is crisscrossed by giant streams and clouds of stars. These are not random alignments, but coherent structures, where the stars all move together on similar orbits. These stellar streams are the unmistakable signatures of gravitational disruption. the visible remnants of smaller dwarf galaxies that have been captured and torn apart by Andromeda's immense tidal forces over billions of years. As a dwarf galaxy is pulled into a larger one, its stars are stripped away from it, forming long, trailing tails in front of and behind it, much like a trail of breadcrumbs. Over time, these streams disperse and merge with the halo, but for a while, they remain as distinct, river-like structures. The discovery of these streams in Andromeda's halo has transformed our understanding of galaxy formation from a theoretical model into an observable, ongoing process. It is a form of galactic archaeology, allowing astronomers to reconstruct Andromeda's merger history by tracing these stellar fossils back to their parent galaxies. This evidence paints a clear picture of hierarchical growth, where large galaxies, like Andromeda, were built up by systematically consuming their smaller cosmic neighbors. As we have seen, one of the most striking differences between Andromeda and our own galaxy is their current rate of star birth. Our Milky Way is a relatively fertile galaxy, consistently producing new stars at a rate of about 1 to 3 solar masses per year. In stark contrast, Andromeda's current star formation rate is significantly lower, estimated to be only about 0.4 solar masses per year. It is a galaxy that is slowly running out of fuel and winding down its stellar production. This red and dead trajectory is common for very massive galaxies, but Andromeda seems to be further along this path than the Milky Way. This difference in activity provides a fascinating snapshot of two different evolutionary stages. With our galaxy still in its active prime, while Andromeda is gracefully entering its a more sedate middle age. Another subtle but important structural difference between the two great spirals is the tightness of their arms. The spiral arms of the Milky Way are thought to be relatively open and loosely wound. Andromeda, by comparison, has very tightly wound spiral arms. They are coiled more closely around the central bulge, giving the galaxy a more compact and less sprawling appearance than other spirals of its size. The precise reason for this difference in pitch angle is not fully understood, but is likely related to the distribution of mass in the galaxy's disk and dark matter halo, as well as its past merger history. This tightly coiled structure affects how density waves propagate through the disk, which in turn influences the pattern and rate of star formation within the arms. Finally, the concentration of stars at the very heart of Andromeda is exceptionally high. The central region of the galaxy is far more densely packed with stars than the equivalent region in the Milky Way. This high central concentration of stars is consistent with its large classical bulge, which is thought to have been formed by the violent scrambling of stellar orbits during major mergers. This dense core is a region of extreme gravity, where the combined pull of millions of stars in close proximity creates a dynamic and chaotic environment. A stark contrast to the more orderly, rotating disk that dominates the outer regions of the galaxy. The anemic rate of star formation in the Andromeda Galaxy has a cascading effect on its entire ecosystem, resulting in a conspicuous scarcity of the celestial objects and phenomena associated with young, massive stars. In our own Milky Way, the spiral arms are studded with brilliant, glowing clouds of reddish light known as HII regions. These are vast clouds of interstellar hydrogen that have been ionized, their electrons stripped away by the intense ultraviolet radiation blasting from clutches of newborn, massive stars embedded within them. They are the visible signposts of active stellar nurseries. In Andromeda, however, these glowing nebulae are few and far between. A census of HII regions in our neighboring galaxy reveals a population that is significantly sparser and fainter than in our own. This dearth of active star-forming sites is a direct consequence of Andromeda's low gas content and reduced star birth rate, painting a picture of a galaxy whose most fertile and creative years are largely in the past. Another class of objects born from the explosive deaths of massive stars is pulsars. These are rapidly rotating, highly magnetized neutron stars, the incredibly dense collapsed cores left behind after a supernova. As a pulsar spins, it sweeps a beam of radio waves across space, much like the beam of a lighthouse. If this beam happens to sweep across the Earth, we detect it as a regular, repeating pulse of radio waves. Because they are the remnants of young, massive stars, active, star-forming galaxies like the Milky Way are expected to be teeming with them. While we have cataloged thousands of pulsars within our own galaxy, dedicated radio surveys of Andromeda have yielded a surprisingly low number of detections. This scarcity is not just due to the immense distance making them difficult to detect. It is also a true reflection of a smaller underlying population. With a lower rate of massive star formation and fewer recent supernovae, Andromeda has simply produced fewer of these exotic stellar remnants in the recent cosmic past compared to the Milky Way. A similar story unfolds when we look for the beautiful, intricate shells of gas known as planetary nebulae. These objects, despite their misleading name, have nothing to do with planets. They are the glowing, expanding shrouds of gas ejected by dying stars of low to intermediate mass, stars like our own sun. As these stars exhaust the fuel in their cores, their outer layers drift off into space and are then illuminated by the hot remnant core, creating spectacular and often symmetrical structures. Because these nebulae are the end-of-life products of a wide range of common stars, their numbers in a galaxy should be proportional to its total stellar population. Given its trillion stars, Andromeda should be filled with them. Yet, surveys have revealed that the number of planetary nebulae per unit of starlight in Andromeda is significantly lower than in the Milky Way. This suggests a subtle but important difference in the stellar populations of the two galaxies, perhaps indicating that the mix of stellar ages and masses in Andromeda is skewed differently than in our own, with a different proportion of its stars currently reaching this final, dramatic phase of their evolution. The organization of young stars in galaxies also follows specific patterns. In the Milky Way, many newborn stars are found in loose groupings called open clusters. These are families of a few dozen to a few thousand stars that all formed together from the same giant molecular cloud. They are gravitationally bound, but only weakly, and they tend to disperse over a few 100 million years as they orbit the galaxy. Famous examples in our vicinity include the Pleiades and Hyades star clusters. In Andromeda, however, such prominent young open clusters are notably less common. This is, again, a direct result of its lower star formation rate. With fewer stellar nurseries actively producing new stars, fewer of these youthful clusters are being formed. The galaxy's stellar population is dominated by older, more solitary stars, rather than these vibrant, youthful families. An even looser and more transient grouping of stars is known as a stellar association. These are extremely large, sprawling collections of very young, massive, and luminous stars, often spanning hundreds of light years. They are so loosely bound that they are not in gravitational equilibrium and are rapidly expanding and dispersing into the surrounding galactic disk. They represent the largest coherent star-forming regions in a galaxy. The grand spiral arms of the Milky Way are traced by numerous, magnificent stellar associations. Andromeda, in keeping with its more quiescent nature, has a significantly lower number of these large-scale associations. Its star formation is not only less frequent, but also appears to be less organized on the grandest scales, lacking the colossal, coordinated bursts of star birth that define the most active regions of our own galaxy. The fundamental fuel for all star formation is cold, dense molecular gas, primarily molecular hydrogen. This gas clumps together into vast, dark structures known as giant molecular clouds. These clouds, which can contain hundreds of thousands of solar masses of gas, are the true stellar nurseries of a galaxy. It is within their dark hearts that gravitational collapse can overcome gas pressure, leading to the formation of protostars. A galaxy's star formation rate is directly tied to its reservoir of this essential raw material. Radio telescope observations, which can detect the faint emissions from molecules in these clouds, have shown that the Andromeda Galaxy has a significantly lower number of giant molecular clouds than the Milky Way. Its gas reserves have been substantially depleted over cosmic time, leaving it with less fuel to power the creation of new generations of stars. This gas depletion is a key factor in its current low level of activity and its slow, inexorable transition towards becoming a more passive, red and dead galaxy. The molecular gas in these clouds represents only one component of a galaxy's total gas reservoir. The most abundant gas is atomic hydrogen, which is more diffuse and fills a much larger volume of the galactic disk. This atomic gas is the primary reservoir from which the colder, denser molecular clouds eventually form. Surveys of the 21-centimeter radio emission from atomic hydrogen in Andromeda reveal that it too has a lower total mass of this gas compared to the Milky Way. It has less raw fuel in its tank. This difference in the fundamental building blocks of star formation is one of the most critical distinctions between the two galaxies and underpins many of the other observed differences in their stellar populations and overall activity levels. Our galaxy, and indeed the entire universe, is permeated by a rain of high-energy particles known as cosmic rays. These are protons, electrons, and atomic nuclei that have been accelerated to nearly the speed of light by some of the most violent events in the cosmos, such as supernova explosions and the accretion disks around black holes. As these particles zip through the galaxy's magnetic field, they emit radio waves, creating a diffuse glow that radio telescopes can detect. The intensity of this glow is a proxy for the density of cosmic rays. Observations of Andromeda show that it has a very low level of this cosmic ray-induced radio emission compared to the Milky Way. This implies that the density of cosmic rays within Andromeda is lower. This makes perfect sense. With fewer supernovae and a less active galactic nucleus, the primary engines that accelerate cosmic rays are less powerful and less numerous in Andromeda, resulting in a less energetic and less irradiated galactic environment. The sum of all these differences points to a fundamentally different life story for each of the two great galaxies. The Andromeda Galaxy appears to have had a different star formation history than the Milky Way. The chemical evidence and stellar populations suggest that Andromeda experienced a much more intense and rapid burst of star formation in its distant past, roughly 2 to 4 billion years ago. This vigorous period created a large fraction of its stars and rapidly enriched its gas with heavy elements. Since then, its star formation has tailed off dramatically. The Milky Way, in contrast, seems to have had a more steady and continuous rate of star formation throughout its life, a slower and more sustained process that continues to this day. Finally, this different history is likely the result of a different merger history. The evidence, from the structure of its large bulge to the timing of its major starburst, suggests that Andromeda experienced its last major merger, a collision with another large galaxy, billions of years ago. This event triggered its massive starburst and ultimately shaped the galaxy we see today. The Milky Way, on the other hand, has had a more tranquil recent past, with its major mergers occurring much earlier in its history, allowing it to evolve more quiescently in recent eons, with only minor fender benders, with small dwarf galaxies to disturb its peace. the grand cosmic web, the filamentary structure of dark matter that's scaffolding the universe, is not uniform. Galaxies are clustered together in groups, clusters, and superclusters, separated by vast, sparsely populated voids. The immediate environment of a galaxy, its proximity to other massive structures, plays a crucial role in its evolution. The Andromeda Galaxy and the Milky Way, despite being gravitational partners in the local group, reside in noticeably different large-scale environments. On the grandest scales, the Andromeda Galaxy is located in a significantly less dense region of the universe than the Milky Way. Our galaxy is situated closer to the Virgo cluster, a massive conglomeration of over 1,000 galaxies located about 50 million light-years away. The immense gravity of this cluster exerts a subtle but persistent influence on our entire local group, a phenomenon known as the Virgo infall. Andromeda, being on the far side of the local group from the Virgo cluster, is less affected by its gravitational pull. This difference in cosmic location means that the Milky Way has likely experienced a slightly different history of infalling gas and dark matter from the surrounding intergalactic medium, which in turn could have influenced its growth and star formation history over billions of years. Within our immediate cosmic family, the local group, the social lives of the two great galaxies also appear to be different. The Milky Way is currently in the process of actively interacting with several of its close companion galaxies. Most notably, the large and small Magellanic Clouds, two of our largest satellites, are on a close pass, their gravitational pull disturbing the outer disk of the Milky Way and triggering streams of gas to flow between the galaxies. Andromeda, in contrast, appears to have fewer close, massive companion galaxies at present. Its most significant satellites, M32 and M110, are smaller and in more stable orbits than the Magellanic Clouds. This relative solitude in recent cosmic history has contributed to Andromeda's more regular and undisturbed appearance, whereas the Milky Way's disk is being actively churned and warped by its boisterous neighbors. The invisible hand that governs the structure and rotation of both galaxies is their vast halo of dark matter. While we cannot see this substance directly, we can map its distribution by observing its gravitational effects on visible matter. Studies of the orbits of satellite galaxies and the hot gas in galactic halos have revealed that the Andromeda Galaxy likely has a different dark matter halo profile than the Milky Way. The evidence suggests that Andromeda's halo has a more chord profile, meaning the density of dark matter becomes relatively flat or constant towards the center. The Milky Way's halo, on the other hand, is thought to have a cuspy profile, where the density of dark matter continues to increase sharply all the way into the galactic center. This structural difference in their invisible scaffolding is a profound one, and is likely a direct result of their different merger histories. a major merger of two galaxies with central black holes can scour out the dark matter in the center, transforming a cuspy profile into a chord one. The chord profile of Andromeda is another strong piece of evidence that it has undergone a more recent and significant major merger than our own galaxy has. The population of small galaxies that orbit a large host galaxy is a direct reflection of its entire assembly history. By taking a census of the satellite galaxies around both Andromeda and the Milky Way, astronomers have found another striking difference. The Andromeda Galaxy's satellite population has a higher fraction of what are known as dwarf spheroidal galaxies, which are small, faint, and gas-poor systems with very little ongoing star formation. The Milky Way's satellite population, in contrast, has a higher fraction of dwarf irregular galaxies, which are more gas-rich and often exhibit active star formation, like the Magellanic Clouds. This difference suggests that Andromeda has been more effective at stripping the gas from its satellite galaxies and quenching their star formation, a process known as environmental quenching. This could be because Andromeda's own halo of hot gas is larger or denser, or because it has simply had more time to process and transform its captive galaxies. This distinction provides a valuable laboratory for studying the complex environmental effects that shape the evolution of small galaxies. The profound mysteries of dark matter and dark energy, the two dominant but completely unknown components of our universe, are among the most pressing problems in modern physics and cosmology. The Andromeda Galaxy, as our closest large galactic neighbor, serves as a crucial test bed for our theories about these enigmatic phenomena. By precisely measuring the motions of its stars, globular clusters, and satellite galaxies, we can create detailed maps of its dark matter distribution. These maps can then be compared with the predictions of different dark matter theories, helping to rule out some models and refine others. Furthermore, by studying the history of the expansion of the local group, a delicate balancing act between the gravitational pull of Andromeda and the Milky Way, and the accelerating expansion of the universe driven by dark energy, we can place constraints on the properties of dark energy itself. Andromeda is not just a beautiful object. It is a fundamental tool in our quest to understand the ultimate nature of the cosmos. For astronomers who study the structure and evolution of galaxies, Andromeda is the gold standard, the benchmark against which all other spiral galaxies are measured. Because of its proximity, we can study it in a level of detail that is impossible for more distant galaxies. We can resolve its individual stars, map its interstellar medium, trace its stellar streams, and analyze its chemical composition with unparalleled precision. This wealth of information allows us to build a comprehensive picture of a typical large spiral galaxy, creating a template that helps us interpret the more limited data we can gather from galaxies millions of light years further away. When a new telescope observes a distant spiral, the first question astronomers often ask is, how does it compare to Andromeda? It is the reference point, the Rosetta Stone, that helps us translate the faint light from the distant universe into a physical understanding of galactic processes. The local group is our home, our cosmic crucible, and the Andromeda Galaxy is its second most important member after our own Milky Way. Understanding the history and future of this small collection of galaxies is a key goal of near-field cosmology. The interactions between Andromeda, the Milky Way, and the dozens of smaller galaxies in the group provide a perfect, manageable model for studying the processes of galaxy formation and interaction that occur throughout the universe. The impending merger of Andromeda and the Milky Way is not just a distant curiosity. It is a preview of the ultimate fate of most galaxies in gravitationally bound groups. By simulating this future collision, we can learn about the fundamental physics of gas dynamics, star formation, and black hole growth that occur during such cosmic train wrecks. The local group, with Andromeda as its co-ruler, is our own backyard laboratory for cosmology. The majestic, swirling form of the Andromeda Galaxy has not only captivated scientists, it has also been a profound source of inspiration for artists, writers, poets, and musicians. Its ethereal beauty, a faint smudge of ancient light in the night sky, evokes a sense of wonder and awe, a connection to something vast and eternal. It has been used in paintings to represent the sublime majesty of the cosmos, in poetry to symbolize the unattainable or the infinite, and in music to create soundscapes of space and time. Like the moon and the stars, it has become a part of our shared cultural lexicon, a powerful symbol that transcends science and speaks to the deeper human need to find meaning and beauty in the universe. More than any other single object outside our own galaxy, Andromeda serves as a powerful symbol of the vastness and beauty of the universe. Its sheer scale, 1 trillion stars, 220,000 light-years across, and its immense distance, a journey of 2.5 million years at the speed of light, provide a humbling and awe-inspiring sense of perspective. It is a visual reminder that our world, our solar system, and even our entire Milky Way galaxy are just small components of a much larger and more magnificent cosmos. Its graceful spiral form is a testament to the elegant and powerful physical laws that shape the universe, from the gravitational collapse of gas clouds to the orbital mechanics of stars. To gaze upon Andromeda is to confront the breathtaking scale and profound beauty of reality. Finally, the Andromeda Galaxy represents a profound and ongoing challenge to our understanding of the universe. Every new observation seems to peel back one layer of mystery, only to reveal deeper and more complex questions. Why is its dark matter halo a different shape than ours? Why did its star formation history differ so dramatically from the Milky Way's? How did its central nucleus and black hole evolve? How many more dwarf galaxies has it consumed? And what can their remnants tell us? These are not just questions about Andromeda. They are fundamental questions about the processes that govern the formation and evolution of all galaxies. Andromeda is a cosmic puzzle, a nearby enigma that constantly pushes the boundaries of our knowledge and forces us to refine and rethink our theories about how the universe works. The Andromeda Galaxy is, in many ways, a grand cosmic mystery that is still being unraveled, one painstaking observation at a time. Despite centuries of study, it continues to hold its deepest secrets close. Each new generation of telescopes reveals another layer of its complexity, posing new questions that challenge our existing models of the universe. We are still piecing together the full story of its violent birth, charting the faint, ghostly streams of stars it has consumed, and trying to understand the intricate dance of its internal dynamics. The precise nature of its central engine, the full extent and composition of its dark matter halo, and the ultimate fate of its satellite galaxies are all subjects of active and intense research. It is a puzzle with 1 trillion pieces, and we have only just begun to assemble the edges. The more we learn, the more we realize how much we do not yet know, making Andromeda not just an object of study, but a driving force for future discovery, a constant and alluring invitation to explore the unknown. For anyone who has stood under a truly dark, moonless sky, far from the glare of city lights, the Andromeda Galaxy is an undeniable wonder of the night sky. It is a subtle but profound sight, a soft, elongated glow that seems to hover in the celestial darkness. To see it with your own eyes is to experience a moment of genuine connection with the cosmos. It is a tangible link to the universe beyond our own stellar neighborhood, a visible confirmation of the island universe theory that so dramatically expanded our cosmic horizons. Its ethereal presence has captivated skywatchers for millennia, a celestial jewel that adds a touch of mystery and grandeur to the familiar star patterns of the autumn sky. It is a spectacle that requires no special equipment, only a dark sky and a curious mind, a universal wonder available to all who take the time to look up. Before the true nature of Andromeda was understood, the debate about the spiral nebula was at the forefront of astronomy. This intellectual struggle was encapsulated in the Great Debate of 1920, a pivotal event that pitted 2 eminent astronomers, Harlow Shapley and Heber Curtis, against each other. Shapley, a brilliant and forceful personality, argued that the Milky Way was the entirety of the universe, and that objects like Andromeda were nearby gas clouds. Curtis, more reserved but equally convinced, presented evidence that Andromeda was a distant, independent galaxy, an island universe in its own right. While the debate itself did not settle the issue, it perfectly framed the central cosmological question of the era and highlighted the profound implications of both possibilities. The eventual resolution in favor of Curtis's view, thanks to Edwin Hubble's work just a few years later, represented a paradigm shift in our understanding of our place in the cosmos, a moment when the universe became infinitely larger and our own galaxy became just one of countless others. The vast majority of galaxies we observe are receding from us, their light stretched to longer, redder wavelengths by the expansion of the universe. This phenomenon, known as redshift, is a cornerstone of modern cosmology. However, the Andromeda Galaxy is a notable exception. It is one of the few galaxies that exhibits a blue shift, meaning its light is compressed to shorter, bluer wavelengths. This is the unmistakable sign of an object that is moving towards us and moving at a considerable speed. This blue shift is a direct result of the powerful gravitational attraction between Andromeda and the Milky Way, a force strong enough to overcome the general expansion of the universe on local scales. The two galaxies are being reeled in by their mutual gravity, a cosmic dance that will culminate in their eventual merger. Andromeda's blue shift is a dynamic and visible indicator of our own galaxy's future, a constant reminder of the powerful, unseen forces that are shaping the destiny of our local group. In the year 2004, astronomers using a network of radio telescopes made a remarkable discovery that provided a new and incredibly precise tool for studying the dynamics of the Andromeda system. They detected the first known water masser in another galaxy. A masser is the microwave equivalent of a laser, a source of intense, coherent microwave radiation that is produced by natural astronomical processes. In this case, the maser was generated by water molecules swirling in a gas cloud within Messier 32, one of Andromeda's key satellite galaxies. These masers are invaluable because they are incredibly compact and bright, acting as precise reference points. By tracking the tiny shifts in the position and frequency of this water masser. Over time, astronomers can measure the motion of M32 with unprecedented accuracy. This allows them to calculate its exact three-dimensional velocity as it orbits Andromeda, which in turn provides crucial data for determining the total mass and distribution of dark matter in the entire Andromeda system. The discovery was a technical tour de force, akin to measuring the speed of a snail on the surface of Mars, and it opened a new window into the gravitational heart of our neighboring galaxy. All of the light, gas, and dust we can see in Andromeda only tells part of its story. The dominant component of its mass is the invisible dark matter that forms its vast halo. By carefully adding up the mass of all its visible components, its 1 trillion stars, its gas, and its dust, and comparing it to the total mass required to explain its rotation curve and the orbits of its satellite galaxies, astronomers have arrived at an estimate for its total mass. The Andromeda Galaxy is thought to weigh in at approximately 1.5 trillion solar masses. That is, its total mass is equivalent to 1.5 trillion times the mass of our own sun. Of this staggering amount, the vast majority, perhaps as much as 90%, is in the form of dark matter. This makes Andromeda not just a city of stars, but a colossal, invisible mountain of mysterious matter, whose gravity dictates the form and fate of everything within it. There is a profound temporal disconnect inherent in observing the Andromeda Galaxy. The light that enters our telescopes or strikes our retinas tonight did not leave Andromeda tonight. It began its immense journey across the void 2.5 million years ago. We are, therefore, seeing Andromeda not as it is today, but as it was 2.5 million years in the past. When that light began its journey, the modern human species did not yet exist. The intervening chasm of time and space is so vast that we are essentially looking into the distant past. Every image of Andromeda is a time capsule, a snapshot of a galaxy as it was when our own ancestors were primitive hominids roaming the African savanna. This temporal lag is a fundamental aspect of astronomy, but it is felt most keenly with Andromeda, our closest large neighbor, a place so near and yet so profoundly separated from us in time. Given its importance as our cosmic twin and a laboratory for galaxy evolution, the Andromeda Galaxy is one of the most intensely studied objects in the entire sky. It has been a prime target for every major astronomical observatory, both on the ground and in space. The Hubble Space Telescope has provided exquisitely sharp images of its stars and clusters. The Spitzer Space Telescope has pierced its dusty veils to reveal the glow of star-forming regions in infrared light. The Chandra X-ray Observatory has pinpointed its black holes and other high-energy sources. Radio telescopes have mapped its cold gas and magnetic fields. This multi-wavelength approach, combining data from across the entire electromagnetic spectrum, has been essential in building the rich, multifaceted understanding of Andromeda that we have today. It is a galaxy that has been scrutinized in every possible way, yet it continues to reward that scrutiny with new insights and fresh mysteries. Ultimately, the Andromeda Galaxy serves as a powerful and humbling reminder of our place in the cosmos and the truly incredible scale of the universe. To contemplate its trillion stars is to appreciate the sheer profligacy of nature. To comprehend its distance is to grasp the immensity of space and time. To witness its slow, inexorable approach is to understand that the universe is not static, but a dynamic, evolving stage on which even galaxies are mortal. It is a celestial touchstone, a connection to the grand cosmic narrative that unfolds far beyond our own small world. It encourages us to look beyond our immediate horizons, to ask fundamental questions about our origins and our destiny, and to stand in awe of the magnificent and complex reality that we are a small but privileged part of. And so, our journey comes to a close. We have traveled across millions of light years and billions of years of history, all to better understand a single, faint smudge of light in our night sky. That distant glow is no longer just a curious celestial cloud. Within its soft, ethereal form, we can now see the echoes of ancient collisions, the light of 1 trillion suns, and the silent, patient pull of a gravity that is, at this very moment, drawing our 2 great galaxies towards an inevitable and spectacular union. The light that began its journey from those spiral arms when our most distant ancestors walked the earth continues to arrive night after night, a constant stream of photons carrying the ghost of a world as it was 2.5 million years ago. It is a story written in starlight, a history of cosmic violence, and a prophecy of a shared destiny. The next time you find yourself under a dark and clear sky, look for that faint and distant cloud. Know that you are not just seeing an object, but a place, a history, and a future. Thank you for listening.